The cabin lights go down, not off, just noticeably dimmer. No announcement accompanies this. The flight attendant presses a control panel switch. The overhead lighting drops to a lower level, and the cabin takes on a different quality. Most passengers register this as an atmospheric shift, a signal that the flight is entering its final phase. Some find it calming. Very few ask why it is happening. The answer has nothing to do with atmosphere or comfort. The lights are dimmed because if something goes wrong in the next few minutes, the difference between eyes that have adapted to low light and eyes that have not could determine whether a person finds the exit or cannot see it. The human eye contains two categories of photoreceptor cells. Cone cells, concentrated in the central retina, handle color vision and fine detail in bright light. Rod cells, distributed across the peripheral retina, handle low-light vision and motion detection in dim conditions. In a brightly lit environment, cone cells are the dominant active system. Rod cells are present but functionally suppressed. Their sensitivity is reduced by the high ambient light levels. When the light level drops suddenly, the visual system must transition from cone-dominated to rod-dominated function. This transition is not instantaneous. It takes time, and the duration is determined by a photochemical process that cannot be accelerated by effort or willpower. Rod cells contain a light-sensitive pigment called rhodopsin. In bright light, rhodopsin is continuously bleached, broken down by photon absorption into its constituent molecules. The rod cells regenerate rhodopsin through a biochemical synthesis pathway, but under bright light conditions, the rate of bleaching exceeds the rate of regeneration, keeping rhodopsin concentrations low and rod cell sensitivity suppressed. When the light level drops, bleaching slows and regeneration catches up. Rhodopsin concentrations rise. Rod cell sensitivity increases. This process, dark adaptation, follows a predictable time course. Initial sensitivity improvement occurs within the first 5 to 10 minutes. Substantial adaptation is achieved within 15 to 20 minutes. Full adaptation, reaching the maximum sensitivity that the rod system can achieve, requires approximately 30 minutes of continuous low-light exposure. The implication for an aircraft emergency is direct. If a cabin that has been brightly lit throughout the cruise phase suddenly loses power on approach due to an electrical failure, a severe landing, or a post-impact fire that disrupts the electrical system, the cabin goes dark instantly. Passengers whose eyes are fully adapted to the bright cabin lighting will experience a period of effective blindness as their visual systems begin the adaptation process. In a fully dark environment with fully dark adapted eyes, a person can navigate by the faint glow of emergency floor lighting, exit markers, and any ambient light entering through windows. In a fully dark environment with unadapted eyes, those same light sources may be invisible for the first critical seconds. 90 seconds is the regulatory standard for emergency evacuation of a commercial aircraft. In a certification test, all occupants must exit through half the available exits within 90 seconds of the signal to evacuate. This standard was derived from analysis of fire development rates in aircraft cabin environments, the time available before conditions become unsurvivable due to smoke and heat. 90 seconds is not a generous margin. In a real emergency with an injured or panicking passenger population, obstacles in the aisle, and exits that may not all be functional, the 90-second window can be consumed quickly. Any factor that reduces the efficiency of passenger movement toward exits represents a real reduction in survivability. Passengers who cannot immediately see where they are going are slower to move, more likely to collide with seats and other passengers, and less able to locate and operate exit doors. Dimming the cabin lights before landing does not complete the dark adaptation process. 30 minutes of low-light exposure would be required for that, and the approach and landing phase of a typical flight lasts 10 to 15 minutes at most. What the dimming achieves is partial adaptation, moving the visual system significantly further along the dark adaptation curve than it would be if the lights remained at full brightness. Partial adaptation is meaningfully better than no adaptation. The difference between fully bright adapted eyes and eyes that have had 10 minutes of low light exposure is substantial in terms of functional vision in a suddenly dark environment. The requirement to open window shades during approach and landing serves a complementary function. With window shades open, passengers seated at windows have direct visual access to the exterior environment. In an emergency landing, the conditions outside the aircraft, fire, water, terrain, structural obstruction, determine which exits are usable and which are not. A passenger who can see that the left side of the aircraft is on fire, or that the right side has come to rest against an embankment, can make an informed decision about which direction to move. Flight attendants positioned at exit doors make the same assessment before opening their assigned door. Opening an exit onto a fire or into water is potentially more dangerous than remaining in the aircraft. Window shades open before landing give both passengers and crew the visual information they need to make these assessments quickly. The instruction to turn off or dim personal electronic devices during approach and landing has the same underlying logic as the cabin light dimming, applied at the individual level. A bright smartphone screen held at reading distance produces a light level that actively drives rhodopsin bleaching in the eyes of the person holding it. A passenger who has been looking at a bright screen until the moment of landing has done precisely the opposite of what the cabin dimming procedure is designed to achieve. They have maintained their eyes in a fully bright adapted state, rather than allowing any dark adaptation to begin. The instruction is not about electromagnetic interference with aircraft systems. It is about preserving the visual capability of the passenger in the event of an emergency. Compliance with the electronic device instruction is imperfect on most flights. Passengers who are unaware of the physiological rationale treat the request as an arbitrary procedural requirement and either ignore it or put the device away briefly before resuming use. Airlines and crew members who explain the reason for the instruction report better compliance than those who simply issue the instruction without context. The information is not confidential or complex. It is straightforward human physiology, but it is almost never communicated to passengers as part of the pre-flight safety briefing. The cabin lighting dimming procedure is not universally applied in identical form across all airlines and all flights. Daytime approaches in good visibility present a different light environment from night approaches. The exterior is brightly lit, and passengers can see clearly through open windows regardless of the cabin lighting level. Some airlines apply the dimming procedure only for night approaches and landings, on the grounds that the dark adaptation benefit is relevant only when the exterior environment is also dark. Others apply it for all approaches as a standardized procedure, regardless of time of day, on the grounds that procedural consistency reduces the risk of the step being omitted when it matters most. The design of aircraft cabin lighting systems has evolved considerably with the adoption of LED technology. Older fluorescent and incandescent cabin lighting systems had limited dimming capability and required a relatively abrupt transition between lighting levels. LED systems can dim smoothly across a continuous range from full brightness to near darkness, and can be programmed to transition gradually over several minutes rather than switching abruptly. This capability allows the dimming procedure to begin earlier in the approach without creating a jarring change in the cabin environment, giving passengers more time at lower light levels and therefore more dark adaptation before landing. Some airlines program their LED cabin lighting to begin a gradual dimming cycle automatically at a defined point in the descent profile, removing the requirement for a crew member to initiate the procedure manually. The procedure will remain in use as long as aircraft cabins are lit, and emergency evacuations must be completed in dark conditions. The biology of dark adaptation is not going to change. The 90-second evacuation standard reflects real physical constraints on how quickly fire and smoke make a cabin unsurvivable, and those constraints are also not going to change. What changes is the sophistication of the systems used to manage the lighting transition and the degree to which the reasoning behind the procedure is communicated to the people it is designed to protect. The switch that dims the cabin lights before every night landing is one of the smallest physical actions taken by a flight crew member during an approach. The preparation it initiates is one of the most consequential, a 10-minute head start on a biological process that cannot be rushed, providing a marginal but real improvement in the visual capability of everyone in the cabin. If the aircraft does not reach the gate in the condition everyone expects, the action takes 1 second. The preparation it provides lasts for the duration of the approach. That ratio, 1 second of crew action, 10 minutes of biological benefit, is characteristic of the best safety procedures, small in execution, significant in effect, and invisible until the moment they are needed.